In October 2022, the James Webb Space Telescope turned its infrared instruments toward one of astronomy's most iconic structures, the Pillars of Creation, and revealed something that fundamentally changed our understanding of these towering columns of gas and dust. What appeared in Hubble's famous 1995 image as three distinct pillars reaching upward through glowing clouds is actually part of a vast star-forming region, extending more than 30 light-years across, with the visible pillars representing only the densest concentrations in a complex three-dimensional landscape that Hubble's visible light cameras could never fully reveal. The true scale of the Pillars of Creation defies the impressions created by decades of viewing Hubble's images. The leftmost pillar, the most prominent and photographed, extends approximately 4 light-years from base to tip, roughly the distance from our Sun to the nearest star system, Alpha Centauri. But JWST's infrared vision penetrated the obscuring dust to reveal that this pillar is not a solitary structure but rather the exposed edge of a much larger molecular cloud complex. Behind and around the visible pillars, JWST detected dozens of additional condensations, embedded protostars, and filamentary structures that were completely invisible to Hubble, revealing that what we've been calling the pillars for nearly 3 decades represents perhaps 10% of the total star-forming material in this region. The measurements are staggering. The entire field captured in JWST's image spans approximately 8 light-years horizontally and contains an estimated 10,000 solar masses of gas and dust, enough material to form thousands of stars if the region weren't being actively photo-evaporated by nearby massive stars. The pillars themselves, which appear as dark silhouettes against glowing background nebulosity in JWST's infrared view, contain approximately 200 solar masses of material concentrated into structures just a few light-years across. This density contrasts the pillars being roughly 100 times denser than surrounding nebular material, is what allows them to temporarily resist intense radiation pressure that is systematically destroying the very structures giving birth to new stars. Dr. Klaus Pontoppidan, JWST project scientist at the Space Telescope Science Institute, described the revelation in stark terms. Hubble showed us a beautiful snapshot in visible light, but JWST has revealed the complete story. The pillars are not isolated structures but rather peaks in a mountain range of star formation. And the scale of the entire complex is far larger and more intricate than we understood from optical observations alone. What makes JWST's observations revolutionary extends beyond simply seeing more structure. The telescope's infrared capabilities enable measuring physical properties that were previously inaccessible. By observing at wavelengths between 0.6 and 28 micrometers far into the infrared where dust becomes transparent, JWST detects newborn stars still embedded in their natal cocoons, measures the temperature and density of gas at various locations throughout the pillars, and traces the three-dimensional structure by observing how different layers of material scatter and emit light at different wavelengths. These measurements reveal that the pillars extend not just vertically as they appear, but also possess substantial depth along our line of sight, creating a complex topography invisible in two-dimensional images. The time dimension adds another layer of revelation. Hubble's 1995 image captured the pillars at one moment, providing no information about how they formed or how rapidly they're changing. By comparing JWST's 2022 observations with Hubble's images from 1995, 2007, and 2014, astronomers can now measure the pillars' evolution directly. The tips of the pillars are being photo-evaporated, literally boiled away by ultraviolet radiation from nearby hot stars at rates approaching 10,000 kilometers per year. At this rate, the iconic structures will be significantly altered within 100,000 years and completely dispersed within a few million years. We're witnessing the pillars during a brief, spectacular phase of their existence, catching them in the act of forming stars while simultaneously being destroyed. The distance to the Pillars of Creation has been refined through multiple measurement techniques to approximately 6,500 light-years from Earth, located in the constellation Serpens. This places the pillars within the Eagle Nebula, also catalogued as Messier 16, a region of active star formation containing the massive star cluster NGC 6611. The young, hot stars in this cluster formed just 1 to 2 million years ago are the very objects whose intense radiation is sculpting and eroding the pillars. The entire nebula spans roughly 70 light-years across, with the pillars occupying a small but prominent region near the nebula's heart where star formation remains vigorously active. Throughout this exploration, we'll examine what JWST's observations reveal about the true three-dimensional structure of the pillars, how infrared vision changes our understanding of what's actually happening in these clouds, why the measured dimensions exceed what visible light observations suggested, and what the pillar's eventual fate tells us about star formation across the galaxy. We'll explore how JWST's measurements of temperature, density, and composition provide insights into the physical processes governing star birth, and how the hundreds of newly detected protostars embedded in the pillars change our estimates of the region's star formation efficiency. Before continuing this journey into one of the universe's most spectacular stellar nurseries, subscribe to this channel and give this video a thumbs up if you're fascinated by how new technology reveals hidden cosmic truths. And here's a question: if you could travel to the pillars of creation and observe them from within, what do you think you would actually see? Comment below with your thoughts. I'll pin the most creative answer. The pillars of creation have captured human imagination since Hubble first revealed them in 1995, becoming perhaps the most reproduced astronomical image in history. But that image, for all its beauty and cultural impact, showed us only a fraction of the story. JWST's observations demonstrate that the pillars are larger, more complex, more active, and more ephemeral than we understood. They're not static monuments but dynamic, evolving structures where the competing processes of star formation and stellar destruction play out on scales that dwarf our solar system and timescales that, while brief cosmically, extend far beyond human civilization's entire existence. The revelation of the pillar's true scale raises profound questions about how we interpret astronomical images. For decades, millions of people viewed Hubble's iconic photograph, understanding it as showing three pillar-like structures in space. That understanding wasn't wrong exactly, but it was incomplete, like viewing a mountain range from one carefully chosen angle. That makes three peaks appear isolated when they're actually part of a vast connected massif. JWST's infrared vision provides the aerial perspective that reveals the full topography, changing our mental model from three pillars to complex star-forming landscape with prominent features. The scale comparison becomes even more striking when contextualized against familiar distances. The tallest pillar, at 4 light-years, extends approximately 38 trillion kilometers, a distance that light, traveling at 300,000 kilometers per second, requires 4 years to cross. If you could somehow travel at the speed of our fastest spacecraft, covering about 17 kilometers per second, traversing the pillar from base to tip would require roughly 70,000 years. These structures operate at scales that reduce human experience to irrelevance. Yet through instruments like JWST, we can measure, map, and understand them with remarkable precision. Now let's begin by understanding the historical context, how Hubble's observations established the pillars of creation as an icon, and what limitations of visible light astronomy shaped our initial understanding of these structures. Hubble's legacy. The Hubble Space Telescope's wide-field and planetary camera to capture the original pillars of creation image during observations conducted in April 1995. The image combined exposures through 3 different filters: 656 nanometers capturing ionized hydrogen emission, 673 nanometers for sulfur emission, and 502 nanometers for ionized oxygen. Then assigned these to red, green, and blue channels to create the false color composite that became instantly iconic. The resulting image showed 3 dark, column-like structures silhouetted against a glowing background of emission nebulosity, with the pillars appearing to rise from a dense cloud base toward regions of brighter emission. Principal investigator Jeff Hester at Arizona State University recognized immediately that the image captured something visually powerful beyond its scientific content. The pillars resembled terrestrial landscapes, towering mesas, carved cliffs, even reaching fingers, creating anthropomorphic associations that made the cosmic scale feel paradoxically accessible. The image was released to the public on April 1, 1995, and within days it had appeared in newspapers and magazines worldwide, quickly becoming what many consider the most famous astronomical photograph ever taken. The scientific value of Hubble's observations extended beyond aesthetic impact. The image revealed that the pillars are regions of dense molecular gas being shaped by photoevaporation, a process where intense ultraviolet radiation from nearby hot stars heats the surface layers of clouds, causing material to boil away and flow outward. The pillars survive because they're denser than surrounding material, resisting erosion longer than the more diffuse nebulosity around them. Small, dark globules visible at the pillar tips represented evaporating gaseous globules, or EGGs, thought to contain protostars still forming within protective cocoons of dust. Hubble's spatial resolution of approximately 0.05 arc-seconds, limited by diffraction through its 2.4 meter primary mirror, allowed resolving structures down to about 0.1 light-years at the Eagle Nebula's distance. This resolution revealed fine details in the pillar surfaces, knots and streamers of material, intricate texture in the dense cloud surfaces, and the smallest EGGs measuring just a few thousand astronomical units across. These details demonstrated that the pillars possess complex small-scale structure superimposed on their large-scale morphology, hinting at turbulent dynamics and active physical processes occurring within the clouds. Follow-up observations in 2007 used Hubble's advanced camera for surveys to recapture the pillars with improved sensitivity and spatial resolution. The new observations revealed additional detail in the pillar surfaces and allowed, for the first time, measuring changes between the 1995 and 2007 images. Jets of material streaming from embedded young stars became visible as faint wisps emerging from several EGGs. The pillar surfaces showed subtle shifts in position, with some features moving outward by measurable amounts over the 12-year baseline. These measurements provided the first direct evidence that the pillars are actively evolving, not static structures frozen in time. The 2014 observations using Hubble's Wide Field Camera 3 produced both visible and near-infrared views, with the near-infrared observations penetrating dust to reveal previously hidden embedded stars. The infrared observations detected more than 70 newly visible stars within the pillar region, suggesting that star formation was more active than visible light observations indicated. However, Hubble's near-infrared capability extended only to about 1.6 micrometers wavelength, sufficient to penetrate moderate dust extinction but still limited compared to longer wavelength infrared observations that would come with JWST. Each Hubble observation refined measurements of the pillar's physical properties. Spectroscopic observations measured the gas temperature at approximately 10,000 Kelvin in the ionized regions surrounding the pillars, decreasing to roughly 100 Kelvin deep within the dense molecular material. Density estimates suggested the pillar cores contain approximately 10,000 hydrogen molecules per cubic centimeter, vastly denser than typical interstellar space with less than one atom per cubic centimeter, but still far more tenuous than Earth's atmosphere with 1,019 molecules per cubic centimeter. The photoevaporation rate became measurable through detailed surface feature tracking. Material at the pillar surfaces flows outward at approximately 10 kilometers per second, driven by heating from ultraviolet radiation. The mass loss rate from photoevaporation totals roughly 0.01 solar masses per year across all three main pillars, seemingly small but accumulating to significant erosion over timescales of hundreds of thousands of years. Calculations suggested the pillars have been photoevaporating for approximately 1 to 2 million years since the nearby massive stars formed, and might persist for another million years before being completely dispersed. Hubble's observations established the pillars as textbook examples of several important astrophysical processes. They demonstrated how radiation pressure from massive stars sculpts molecular clouds, creating complex morphology through differential photoevaporation. They showed that star formation can occur in actively eroding clouds. The process that destroys the cloud also triggers collapse in dense regions, creating a feedback loop where massive star formation both enables and limits subsequent star formation. They provided clear visual evidence for theoretical predictions about how massive stars reshape their environments. However, Hubble's visible and near-infrared observations face fundamental limitations. Dust extinction at visible wavelengths is severe. Light at 500 nanometers is attenuated by a factor of roughly 10 for every magnitude of visual extinction. The pillars of creation have visual extinction exceeding 10 magnitudes in their densest regions, meaning visible light is dimmed by factors exceeding 10 billion. Even Hubble's near-infrared observations at 1.6 micrometers face extinction factors of thousands in the pillar cores. This opacity means that Hubble could observe only the pillar surfaces, seeing no more than 1% of the way into the structures. The three-dimensional structure remained largely unknown from Hubble observations. The pillars appear as two-dimensional projections on the sky, with no direct information about whether they extend primarily along our line of sight or perpendicular to it. Their true volumes, masses, and three-dimensional geometries could only be estimated through indirect arguments about cloud structure and assumptions about symmetry. Whether the region contains additional pillar structures oriented such that we view them edge-on, rendering them invisible as distinct columns, remained unanswerable with visible light observations. The stellar population within the pillars remained mostly hidden. While the 2014 infrared observations detected 70 embedded stars, these represented only the most massive, luminous protostars that were minimally obscured. The full population of forming stars, particularly lower-mass stars that would dominate numerically, remain indetectable. Without knowing how many stars are actually forming, calculating the region's star formation efficiency and comparing it to theoretical predictions was impossible. The pillars might be extraordinarily efficient star factories or relatively inefficient. With most of their mass destined to be photoevaporated without forming stars, the physical conditions deep within the pillar's temperature, density variations, molecular composition, and magnetic field structure remained largely unmeasured. Surface observations constrain conditions at the pillar exteriors, but the interiors where star formation actually occurs were inaccessible to Hubble's instruments. Weather conditions vary substantially with depth, whether temperature and density gradients exist, and how turbulence affects the internal structure all remain open questions requiring observations at wavelengths where dust becomes transparent. Hubble's legacy for the pillars of creation is nonetheless profound. The observations established these structures as archetypes of photoevaporated molecular clouds, demonstrated that star formation occurs in hostile environments pervaded by destructive radiation, and captured public imagination in ways that few astronomical images have. The 1995 image hangs in classrooms, adorns textbooks, and appears on magazine covers and museum displays worldwide. It represents, for many people, what deep space looks like, an association that shapes how millions conceptualize the universe beyond Earth. The scientific understanding built from Hubble observations provided essential context for interpreting JWST results. The photoevaporation framework, the identification of embedded protostars, the measurements of surface conditions, and the temporal evolution tracking all established baseline knowledge against which new infrared observations could be compared. JWST's observations don't replace Hubble's but rather complement them, with visible and infrared wavelengths revealing different aspects of the same physical structures and processes. The decades between Hubble's first observations and JWST's launch saw tremendous progress in understanding star formation generally, much of it informed by the pillars of creation as inaccessible. Well-studied example, theoretical models of triggered star formation, numerical simulations of photoevaporation, and statistical studies of young stellar objects all benefited from the detailed constraints Hubble provided. The pillars became a benchmark case. Any theory of massive star feedback on molecular clouds had to reproduce the observed pillar morphology, photoevaporation rates, and embedded stellar population. When JWST finally observed the pillars in 2022, astronomers approached the data with both excitement and trepidation. Excitement because infrared observations promised to reveal what Hubble couldn't see: the pillar interiors, the full stellar population, the three-dimensional structure. Trepidation because the iconic status of Hubble's image created expectations that JWST's different wavelength coverage and appearance might challenge. In the event, JWST's observations exceeded expectations, revealing complexity and scale that transformed understanding while confirming the basic physical Picture Hubble established. Webb's revolution. The James Webb Space Telescope observed the pillars of creation in October 2022 using its near-infrared camera NIRCam and mid-infrared instrument MIRI, covering wavelengths from 0.6 to 21 micrometers. This wavelength range spans the near-infrared, where young stars shine brightly through moderate dust extinction, to the mid-infrared, where dust itself glows thermally. The multi-wavelength coverage allows simultaneously observing stars embedded in the pillars and the dust structure of the pillars themselves, providing complementary views that together reveal the region's complete architecture. NIRCam observations used 6 filters spanning 0.9 to 4.4 micrometers, with each filter capturing light at specific wavelengths sensitive to different physical processes. The 0, 9 and 1.15 micrometer filters detect stellar photospheres, the surfaces of young stars, while the 2.0 and 3.35 micrometer filters capture emission from shocked molecular hydrogen, where stellar wind and jets impact surrounding material. The 4.44 micrometer filter detects ionized hydrogen emission and also captures scattered starlight reflected from dust grains, revealing cloud structure through illumination gradients. MIRI observations at 7.7 and 21 micrometers measure thermal emission from dust at different temperatures. The 7.7 micrometer filter captures emission from polycyclic aromatic hydrocarbons, complex carbon molecules that fluoresce when excited by ultraviolet starlight, tracing the interface between ionized and molecular gas. The 21 micrometer filter detects thermal continuum from cool dust at temperatures around 100 to 200 Kelvin, revealing the coldest, densest regions where the most obscured star formation occurs. These wavelengths are completely inaccessible from ground-based telescopes due to Earth's atmospheric absorption. The technical capabilities enabling these observations represent dramatic advances over Hubble. JWST's primary mirror spans 6.5 meters diameter compared to Hubble's 2.4 meters, providing nearly 3 times better angular resolution at equivalent wavelengths and collecting -1 times more light, operating in the infrared at wavelengths 2 to 20 times longer than Hubble's visible observations. JWST achieves angular resolution of approximately 0.06 arcsecons at 2 micrometers, comparable to Hubble's visible light resolution, but at wavelengths where dust extinction is reduced by factors of 10 to 100. The sensitivity improvement exceeds even the larger aperture. Suggests JWST's detectors achieve near-perfect quantum efficiency, converting virtually every detected photon to an electronic signal. The telescope's location at the ultra-Lagrange point and extensive sun shields maintain temperatures around 40 Kelvin, reducing thermal background to negligible levels compared to warmer telescopes. The combination of large aperture, efficient detectors, and low background enables JWST to detect sources approximately 100 times fainter than Hubble can observe in near-infrared wavelengths, revealing young stars still deeply embedded in natal cocoons. The observing strategy involved mapping the entire pillars of creation region with overlapping pointings to create a mosaic covering approximately 8 by 8 light years. Each pointing used multiple short exposures to avoid saturating on bright stars, plus longer exposures to reach faint embedded protostars. The total integration time exceeded 10 hours across all filters and pointings, accumulating sufficient signal-to-noise ratio to detect sources thousands of times fainter than the brightest stars in THE field. This depth enables creating a nearly complete census of forming stars down to masses approaching 1/10 that of the Sun. Data processing presented significant challenges due to the field's complex structure and wide range of brightness scales. The brightest background stars are millions of times brighter than the faintest embedded protostars, requiring careful handling to avoid artifacts where bright star diffraction patterns might mask faint nearby sources. The nebular emission contributes substantial diffuse background that must be modeled and subtracted to reveal point sources. Multiple processing pipelines were employed, with results compared to ensure detected sources and measured brightnesses were robust against processing choices. The resulting images revealed structure invisible to Hubble with startling clarity. The pillars appear not as dark silhouettes but as semi-transparent features with complex internal structure. Hundreds of point sources, young stars previously hidden by dust, appear throughout the pillar interiors, with the highest concentrations near the pillar tips where Hubble detected EGGs. The pillar surfaces show intricate filamentary structure, with tendrils of material extending from the main columns and knots of enhanced density appearing at various locations. The three-dimensional architecture becomes apparent through differential extinction background. Stars dim to varying degrees depending on the column density of intervening material, perhaps most dramatically. JWST's images reveal that the pillars are not isolated structures. Additional columns, pillars, and condensations appear throughout the field, some oriented such that their narrow profiles were invisible to Hubble, others to dust embedded to appear in visible light. The region resembles a complex topography of peaks, valleys, and plateaus rather than three discrete pillars. This changes the conceptual model from three special structures to complex landscape with three particularly prominent features. The infrared colors of embedded sources provide diagnostic information about their evolutionary states. The youngest protostars appear extremely red, bright at 4 micrometers but faint or invisible at shorter wavelengths. These sources are Class 0 and Class 1 protostars, objects still accumulating most of their final mass, surrounded by thick envelopes of infalling material. More evolved sources show bluer colors, appearing at shorter wavelengths as their envelopes thin and more stellar photospheric light escapes. The bluest sources are Class 2 and Class 3 stars, young stellar objects that have largely dispersed their envelopes and now resemble main sequence stars with or without residual circumstellar disks. The stellar population statistics derived from JWST observations dramatically revise upward the number of forming stars. NIRCam detected approximately 300 sources within the main pillar region, more than 4 times the number Hubble's infrared observations found. Extending the analysis to the broader field encompassing the full 8 light-year mosaic brings the total to over 1,000 young stellar objects. This population suggests the region is forming stars at a rate approximately 5 times higher than estimates based on Hubble observations, which missed the majority of embedded protostars due to extinction limitations. The mass distribution of detected stars follows expectations from theoretical stellar initial mass functions, with most sources having masses between 0.3 and 3 solar masses. However, JWST's detection limits still don't reach the lowest mass stars, brown dwarfs, and substellar objects with masses below 0.08 solar masses. Extrapolating from the detected population suggests the total stellar population, including undetected low-mass objects, might exceed 2,000 forming stars within the 8 light-year region. This makes the pillars of creation one of the most active star-forming regions within several thousand light-years of Earth. Spectroscopic follow-up observations using JWST's near-infrared spectrograph measured detailed chemical composition and physical conditions for selected embedded sources. The spectra show strong molecular hydrogen emission lines indicating active shock heating from stellar winds impacting surrounding material. Water ice absorption features at 3.0 micrometers confirm that many protostars remain embedded in ice-rich envelopes. Carbon monoxide absorption at 4.67 micrometers provides temperature and density diagnostics showing gas temperatures between 50 and 300 Kelvin at densities of 105 to 107 molecules per cubic centimeter in the pillar cores. The MIRI observations at 7.7 and 21 micrometers reveal the coolest dust emission, tracing the densest molecular cloud cores where the youngest protostars are forming. These images show the pillars as bright emission features rather than dark absorption columns, with peak emission corresponding to the highest column densities. The spatial distribution of dust emission allows measuring the three-dimensional structure through tomographic techniques by analyzing how emission varies with wavelength and comparing with radiative transfer models. Astronomers can reconstruct the density distribution along the line of sight. Comparison between NIRCam and MIRI images demonstrates the wavelength-dependent appearance dramatically. In NIRCam's shortest wavelength filters near 1 micrometer, the pillars appear mostly opaque, resembling Hubble's visible light appearance. At intermediate wavelengths around 2 micrometers, the pillars become semi-transparent with significant internal structure visible. At MIRI's longest wavelengths beyond 10 micrometers, the pillars essentially disappear as absorbing features and instead appear as emission sources, with the densest regions glowing most brightly in thermal radiation from cool dust. This wavelength progression reveals that seeing through dust is not an all-or-nothing proposition, but rather a gradual transition. At visible wavelengths, one can see essentially nothing inside the densest regions. At 1 micrometer, perhaps 1% of the way through. At 2 micrometers, 10 to 20%. At 5 micrometers, halfway through even dense cores. At 10 micrometers and beyond, dust becomes largely transparent, and one observes the entire column depth integrated along the line of sight. JWST's multi-wavelength coverage samples this progression, enabling three-dimensional reconstruction impossible with any single wavelength. The observational revolution JWST provides extends beyond simply better images to fundamentally new data types, enabling different scientific questions. With Hubble, astronomers could ask what the pillar surfaces look like and how they're changing. With JWST, they can ask what's happening deep inside the pillars, how many stars are forming and at what rate, how conditions vary through the three-dimensional volume, and how the nascent stellar population will eventually disperse or destroy its parent cloud. These questions require the infrared access and sensitivity only JWST provides. True dimensions, the physical scale of the pillars of creation, becomes quantifiable through careful measurement of JWST's images combined with accurate distance determination to the Eagle Nebula. The distance has been refined through multiple independent methods. Main sequence fitting of the cluster NGC 6611 yields approximately 6,500 light-years. Spectroscopic parallax of individual cluster members gives 6,400 light-years. And statistical analysis of reddening and extinction suggests 6,600 light-years. The weighted average of 6,500 light-years with uncertainty of roughly 300 light-years provides the baseline for converting angular sizes to physical dimensions. At this distance, 1 arc-second on the sky corresponds to approximately 0.03 light-years, or about 2,000 astronomical units. JWST's images span approximately 4 arc-minutes on a side, 240 arc-seconds, translating to roughly 7 light-years. Within this field, the main pillar structures extend between 2 and 4 light-years from their bases in the dense molecular cloud to their tips pointing toward the ionizing radiation sources. The leftmost pillar, the tallest and most prominent in both Hubble and JWST images, measures approximately 4.2 light-years from base to tip based on JWST's high-resolution morphology measurements. This 4 light-year extent provides context for comprehending the scale. Light from the pillar's base, emitted today, would reach its tip in the year 2029. A spacecraft traveling at the speed of Voyager 1, currently humanity's fastest object at about 17 kilometers per second, would require approximately 70,000 years to traverse the pillar lengthwise. The pillar contains roughly 4 times the distance separating our Sun from its nearest stellar neighbor, compressed into a single coherent structure shaped by radiation pressure and gravitational forces. The lateral dimensions perpendicular to the pillar axes measure between 0.5 and 1.5 light-years for the main columns. The pillars are thus roughly 3 to 8 times longer than they are wide, giving them aspect ratios between 3 to 1 and 8 to 1. These proportions create the columnar appearance that inspired their name, though the structures are far from perfectly cylindrical. Cross-sections vary substantially along the pillar lengths, with the widest points typically occurring near the bases where they merge into the broader molecular cloud, and narrower wastes appearing at intermediate heights before widening again near some pillar tips. The volume calculations require accounting for the three-dimensional structure beyond simple geometric approximations. The pillars are not uniform cylinders but rather irregular columns with complex surface morphology. Detailed volumetric analysis using JWST's multi-wavelength observations suggests the main leftmost pillar contains approximately 1.5 times 1056 cubic centimeters, roughly 80 solar masses. If the mean density is 100 for molecules per cubic centimeter, the total volume of all 3 main pillars plus associated structures amounts to approximately 1056 cubic centimeters, containing roughly 200 solar masses of material. These mass estimates agree reasonably well with independent measurements using dust emission at far infrared and submillimeter wavelengths. The Herschel Space Observatory observed the Eagle Nebula region at 70 to 500 micrometers, measuring thermal emission from cool dust that traces total column density. Converting from dust emission to total mass requires assuming a dust-to-gas ratio of approximately 1 to 100 for every gram of dust. There are 100 grams of gas. The Herschel-derived mass for the pillar region is approximately 180 solar masses, consistent with the 200 solar masses estimated from JWST's volumetric analysis. The depth of the pillars along our line of sight, how far they extend into the page of JWST's two-dimensional images, remained uncertain from Hubble observations, but becomes measurable through JWST's infrared observations. By analyzing how background stars dim progressively when viewed through different portions of the pillars, and comparing this extinction map with dust temperature measurements from MIRI observations, astronomers can constrain the three-dimensional density distribution. These analyses suggest the pillars extend between 1 and 2 light-years along the line of sight, roughly comparable to their lateral widths. This finding indicates the pillars are not highly elongated structures oriented nearly perpendicular to our line of sight, nor are they thin sheets aligned parallel to it. Instead, they're roughly equidimensional column structures with comparable dimensions in all three spatial directions. This geometry makes physical sense. The photoevaporation process shaping the pillars operates from specific directions determined by the ionizing star locations, carving the pillars roughly perpendicular to the direction of incoming radiation. Our viewing angle happens to show this geometry in profile rather than face-on or edge-on. The surface area calculations become important for understanding photoevaporation rates. A pillar 4 light-years tall and 1 light-year wide, with comparable depth, has total surface area approximately 5 kd square centimeters, about 3 square light-years. With photoevaporation velocity of 10 kilometers per second, the volume of material evaporated per year is roughly 1.6 times K at cubic centimeters. At density 100 for molecules per cubic centimeter, this corresponds to mass loss of approximately 0.003 solar masses per year from the leftmost pillar alone. Across all pillar structures, total photoevaporative mass loss approaches 0.01 solar masses per year. The comparison between pillar volumes and the broader molecular cloud context reveals that the pillars represent density enhancements of factors between 10 and 100 over typical molecular cloud material. The surrounding Eagle Nebula molecular cloud has mean density around 100 to 300 molecules per cubic centimeter and total mass of approximately 10,000 solar masses spread across 70 light-years. The pillars contain just 1% of this mass but occupy less than 0.01% of the volume, making them among the densest structures in the nebula. These density contrasts explain why the pillars can resist photoevaporation longer than surrounding material. Lower density gas photoevaporates on timescales of 10,000 to 100,000 years. Material 100 light-years from ionizing stars experiences photoevaporation rates of roughly 0.1 parsecs per million years. Denser pillar material resists erosion longer, but eventually succumbs to the relentless radiation pressure. The current pillar masses and measured erosion rates suggest lifetimes around 1 to 2 million years before complete dispersal. The internal structure revealed by JWST shows density variations within individual pillars spanning at least another factor of 10. The densest cores, the sites of active star formation traced by embedded protostars, reach densities exceeding 106 molecules per cubic centimeter. These cores are gravitationally bound, contracting under their own weight to form stars. The surrounding lower density envelope at 104 to 105 molecules per cubic centimeter provides the reservoir feeding continued core collapse and also represents the material being most rapidly photoevaporated. Spatial scales of structure within the pillars span from the largest features down to JWST's resolution limit. The main pillar columns measure light-years in extent. Prominent knots and substructures visible along the pillar surfaces measure 0.1 to 0.3 light-years, still enormous by solar system standards, comparable to thousands of astronomical units. The finest details resolved in JWST images correspond to approximately 0.01 light-years or about 600 astronomical units, roughly 15 times the distance from the Sun to Neptune. Structure certainly exists at smaller scales, but it remains unresolved even in JWST's extraordinary images. The temporal scales governing pillar evolution provide perspective on their transient nature. The pillars likely began forming roughly 1 to 2 million years ago when the massive stars in NGC 6611 turned on and began ionizing their surroundings. The photoevaporation process carved the current pillar morphology over this time frame, with the structures we observe representing a moment in ongoing evolution. Based on current erosion rates, the pillars will be substantially altered within 100,000 years. Their tips will recede by approximately 1 light-year. New tips will form as underlying dense cores are exposed, and the overall morphology will shift as material is systematically removed. On timescales of several million years, the pillars will be completely dispersed. The material currently in the pillars will either have formed into stars with perhaps 5 to 10% of the mass ending up in stellar form, or will have been photoevaporated and ionized, contributing to the hot, diffuse gas filling the nebula. The embedded protostars detected by JWST will have emerged from their dusty cocoons, dispersed their circumstellar disks, and settled onto the main sequence as normal stars. The spectacular pillar morphology we observe today will be gone, leaving only the stellar population as evidence that star formation once occurred here. This impermanence adds poignancy to the observations. We're fortunate to observe the pillars during this brief, visually dramatic phase of their existence after they've been carved into spectacular columns but before erosion destroys them completely. Had we observed the region 1 million years ago, before photoevaporation began, we would have seen a more uniform molecular cloud without the distinctive pillar structures. 1 million years hence, we'll see dispersed gas and a young star cluster, with little remaining evidence of the pillars that form the cluster members. The scale revelations from JWST transform the pillars of creation from 3 isolated structures to a complex star-forming region with prominent features embedded in an extensive landscape. Understanding that what we've called the pillars for nearly 3 decades represents a small fraction of the total system reshapes how we think about the Eagle Nebula and similar regions. The pillars are markers. They indicate where particularly dense material concentrates and where star formation occurs most actively, but they're not the full story of this stellar nursery. Infrared revelation. Infrared wavelengths reveal the pillars of creation in fundamentally different ways than visible light because of how radiation interacts with interstellar dust. Dust grains, microscopic particles of silicates, carbonaceous material, and ices absorb and scatter light with efficiency that depends strongly on wavelength. At visible wavelengths around 500 nanometers, dust grains with typical sizes around 0.1 micrometers scatter and absorb light very efficiently. The cross-section for interaction exceeds the grain's geometric size by factors of several, making dust extraordinarily opaque to visible light. This is why the pillars appear dark in Hubble images. The dust blocks background light and prevents internal light from escaping. At infrared wavelengths, the interaction changes dramatically. The efficiency of scattering and absorption decreases approximately as wavelength to the -1 power. Doubling wavelength reduces opacity by a factor of 2. At 2 micrometers, dust opacity is roughly 5 times lower than at visible wavelengths. At 10 micrometers, opacity drops by another factor of 5. By 20 micrometers, the opacity is approximately 100 times lower than at visible wavelengths, making clouds that are completely opaque visibly become largely transparent. This wavelength dependence is described by extinction laws, with the ratio of infrared to visible extinction following empirically determined relationships. The physical reason for decreasing opacity involves particle size relative to wavelength. When wavelength greatly exceeds particle size, radiation doesn't see individual grains effectively. It passes between them with minimal interaction. Since typical dust grains measure 0.1 to 0.3 micrometers, visible light at 0.5 micrometers interacts strongly, while 10 micrometer infrared radiation interacts much more weakly. This size-wavelength relationship governs why longer wavelengths penetrate dust more effectively. JWST's near-infrared observations at 0.9 to 4.4 micrometers reduce extinction by factors of 5 to 50 compared to visible light, allowing observation into pillar interiors that Hubble couldn't access. A region with 10 magnitudes of visual extinction reducing visible light by a factor of 10 billion has only 2 to 3 magnitudes of extinction at 2 micrometers, corresponding to dimming factors of 6 to 15. This transforms completely opaque regions into moderately transparent ones, revealing embedded stars and internal structure invisible to Hubble. The MIRI observations at 7 to 21 micrometers go further, penetrating even dense cores that remain opaque at near-infrared wavelengths. At these wavelengths, extinction becomes negligible except in the very densest regions. Additionally, at these longer wavelengths, the dust itself begins emitting thermally rather than simply absorbing and scattering background light. Dust grains at temperatures between 50 and 300 Kelvin emit peak radiation at wavelengths between 10 and 60 micrometers, matching MIRI's coverage and enabling direct measurement of dust temperature and column density. The multi-wavelength infrared observations allow three-dimensional tomography of the pillar structure. Different wavelengths penetrate to different depths, with shorter wavelengths showing primarily surface features and longer wavelengths revealing progressively deeper layers. By comparing images at multiple wavelengths and using radiative transfer models to interpret the differences, astronomers can reconstruct the density distribution along the line of sight. This technique, called extinction mapping or dust tomography, has become powerful with JWST's unprecedented multi-wavelength infrared coverage. The specific technique involves measuring how background stars dim at different wavelengths when viewed through various portions of the pillars. A background star seen through low column density material might be dimmed by half a magnitude at 2 micrometers but immeasurably at 10 micrometers. The same star viewed through higher column density might be dimmed by 3 magnitudes at 2 micrometers and 1 magnitude at 10 micrometers. The ratio of extinction at different wavelengths constrains the total column density and the dust properties along that sight line. Repeating this measurement for hundreds of background stars samples the pillar structure at many locations. JWST's observations reveal temperature gradients within the pillars that Hubble couldn't detect. The pillar surfaces exposed to ionizing radiation reach temperatures of several hundred Kelvin, warm enough to emit detectable near-infrared radiation. The interiors cool to 50 to 100 Kelvin, too cold for near-infrared emission but glowing in mid-infrared. The cores where protostars form reach even lower temperatures around 20 to 30 Kelvin, emitting primarily at far infrared and sub-millimeter wavelengths beyond JWST's range. This temperature structure creates stratification visible in multi-wavelength images. The chemical composition becomes measurable through infrared spectroscopy. Different molecules absorb and emit at characteristic wavelengths throughout the infrared spectrum. Water ice shows strong absorption at 3.0 micrometers. Carbon dioxide ice absorbs at 4.7 micrometers. Molecular hydrogen emits at 2.12 and 2.5 micrometers. Carbon monoxide absorbs at 4.67 micrometers. JWST's near-infrared spectrograph obtains spectra of numerous positions within the pillars, revealing the molecular inventory and its spatial distribution. The water ice measurements are particularly informative. Ice forms on dust-grained surfaces when temperatures drop below approximately 150 Kelvin and sufficient oxygen and hydrogen exist to form water molecules. The strength of ice absorption features indicates that grains in the pillar interiors are heavily ice-coated, with ice mantles comprising 10 to 50% of total grain mass. This ice reservoir will be incorporated into forming planetary systems around embedded protostars, eventually contributing to comets and possibly oceans on terrestrial planets. The detection of shocked molecular hydrogen emission traces where stellar winds from embedded protostars impact surrounding material. Young stars generate powerful wind streams of particles, flowing outward from stellar surfaces at speeds of hundreds of kilometers per second. When these winds collide with dense molecular material, shock waves heat the gas to thousands of Kelvin, exciting molecular hydrogen to emit strongly at 2.12 micrometers. JWST images show numerous shocked regions as bright knots and filaments, particularly near embedded protostar locations, mapping the energetic feedback from star formation. Polycyclic aromatic hydrocarbons detected in MIRI observations at 7.7 micrometers trace the photodissociation region's interfaces between ionized and molecular gas, where ultraviolet radiation is absorbed. These complex carbon molecules form in molecular clouds and are destroyed by intense radiation, so they concentrate at the transition zones. MIRI images show PAM emission outlining the pillar surfaces, clearly delineating where ultraviolet photons from NGC 6611 stars encounter the dense pillar material. This emission provides an independent tracer of pillar morphology complementing the dust extinction and emission maps. The infrared color variations across JWST's images encode physical information. Regions appearing red and false color composites combining multiple infrared filters indicate cool dust or heavily embedded protostars. Blue regions indicate hotter material or less obscured stars. Gradients in color trace temperature and density variations through the pillars. Quantitative color analysis uses brightness ratios at different wavelengths to measure properties including dust temperature, extinction, and protostar evolutionary class. The embedded protostar population revealed by infrared observations shows spatial clustering indicating that star formation proceeds hierarchically. Rather than forming uniformly throughout the pillars, stars form preferentially in small groups or clusters where material has reached critical densities. JWST detects these groupings as concentrations of embedded sources, with typical groups containing 5 to 20 protostars spanning regions of 0.05 to 0.1 light years. This clustering suggests that molecular cloud fragmentation occurs on multiple scales, producing stellar groups rather than isolated individual stars. The mass function of detected protostars. The distribution of stellar masses appears consistent with the initial mass function observed for field stars, with most stars having masses between 0.3 and 1.0 solar masses, and fewer higher mass stars following a power law distribution. However, JWST's detection limits prevent measuring the mass function for stars below approximately 0.2 solar masses. Whether the IMF continues to lower masses or turns over remains uncertain, requiring even deeper infrared observations or longer wavelengths of millimeter observations to detect the coldest, least massive protostars. The disk fraction among embedded sources provides insights into planet formation potential. Circumstellar disks flattened structures of gas and dust orbiting young stars are the sites where planets form. JWST's infrared observations detect excess emission at longer wavelengths from these disks, allowing measurement of what fraction of protostars possess disks. Preliminary analysis suggests approximately 70% of detected protostars show evidence for circumstellar disks, indicating that planet formation is likely common among the stellar population emerging from the pillars of creation. The comparison between infrared and visible wavelength views highlights how wavelength selection shapes understanding. Hubble's visible light images show the pillars as dark, imposing structures silhouetted against glowing emission, emphasizing the pillars as obstacles to light, solid and impenetrable. JWST's infrared images show them as semi-transparent, complex, populated with embedded stars, emphasizing the pillars as active stellar nurseries, more cloud than mountain. Both views are valid representations of physical reality, but they suggest different metaphors and inspire different questions about these cosmic structures. Star nurseries. Star formation within the pillars of creation proceeds through gravitational collapse of dense cores within the molecular cloud, triggered and influenced by the radiation environment that simultaneously sculpts the pillars and compresses material to critical densities. The process begins when regions within the pillars reach sufficient density, approximately 105 key molecules per cubic centimeter, that self-gravity overcomes turbulent pressure and magnetic field support. These critical densities correspond to masses around 0.5 to solar masses concentrated within volumes measuring roughly 0.01 light-years across. The triggering mechanism linking pillar photoevaporation to star formation involves radiation-driven compression, as ultraviolet photons from NGC 6611 stars heat the pillar surfaces. Heated material expands and flows away, creating pressure that compresses underlying layers. This compression increases density, and if initial density was already marginal for gravitational instability, the compression can push material over the threshold into collapse. Numerical simulations of photoevaporating clouds show that compression can enhance star formation efficiency by factors up to 5 compared to isolated cloud evolution. The collapse timescale depends on the initial core density, for a core at 105 molecules per cubic centimeter. The free fall time, how long material takes to collapse under its own gravity without support, is approximately 100,000 years. Higher density cores at 106 molecules per cubic centimeter collapse in about 30,000 years. Observations of the embedded protostar population show objects at various evolutionary stages from deeply embedded class 0 protostars just beginning collapse to more evolved class 2 sources with thin residual disks, indicating that collapse has been ongoing for at least several 100,000 years. The early collapse phase produces a class 0 protostar, an object where most mass remains in an infalling envelope rather than in the central stellar core. These objects are extremely faint at visible and even near-infrared wavelengths because dense surrounding material absorbs nearly all stellar radiation. JWST detects class 0 sources through their infrared emission at wavelengths beyond 4 micrometers, where they appear as very red sources, bright in mirror images but faint or invisible in shorter wave NGTH NIRCam images. Approximately 50 candidate class 0 protostars were identified at JWST's observations, representing the youngest forming stars. As collapse continues, the central core grows by accreting material from the surrounding envelope. The infall rate typically reaches 10 to 5 to 10 to 4 solar masses per year during the class 0 phase, meaning the protostar gains 1 solar mass in roughly 10,000 to 100,000 years. This rapid accretion releases gravitational energy as infalling material impacts the growing stellar surface, producing luminosity that can exceed what the star will eventually generate through nuclear fusion. The accretion luminosity heats surrounding material, making protostars detectable despite their youth. The class 1 phase follows when the envelope mass drops below the stellar core mass as accretion proceeds. Class I sources appear brighter at near-infrared wavelengths than class 0 objects because less envelope material obscures the central source. JWST detected approximately 150 class 1 protostars within the pillar region, identified by their infrared colors showing significant excess emission at wavelengths beyond 2 micrometers, but also detectable at shorter wavelengths. These sources represent protostars that have formed most of their final stellar mass but retain substantial circumstellar material. Disk formation occurs naturally during collapse as infalling material conserves angular momentum. Even slowly rotating cores possess enough angular momentum that material cannot fall directly onto the central star without first entering orbit. The accumulating orbiting material forms a circumstellar disk, a rotating, flattened structure where viscous transport gradually moves material inward while transporting angular momentum outward. Disk sizes during the class 0 and class 1 phases measure tens to hundreds of astronomical units, resolved in some JWST images as slightly extended sources rather than point sources. The class 2 phase begins when the envelope has largely dispersed and the star is optically visible, though still surrounded by a substantial circumstellar disk. These sources show strong near-infrared emission from stellar photospheres plus excess emission at longer wavelengths from warm dust in the inner disk. JWST detected approximately 100 class 2 sources within the pillar region, recognizable by their blue near-infrared colors combined with red colors at longer wavelengths. The disks around class 2 stars are where planet formation actively occurs through dust grain coagulation and planet simul-assembly. Stellar outflows and jets provide another diagnostic of active star formation. Young stars generate powerful collimated outflow streams of material ejected along the stellar rotation axis at speeds of 100 to 300 kilometers per second. These outflows clear cavities through the surrounding envelope and shock heat ambient material where they impact clouds. JWST images show numerous outflow features as elongated structures emanating from embedded protostars. visible through shock molecular hydrogen emission at 2.12 micrometers, measuring outflow. Morphology and dynamics provides insights into protostellar masses, ages, and accretion rates. The statistics of the detected protostar population allow estimating star formation rates and efficiencies. The approximately 300 protostars span evolutionary timescales totaling roughly 1 million years, the combined duration of class 0, I, and 2 phases. This suggests star formation has been occurring at roughly 0.003 solar masses per year within the main pillar structures, given that the pillars contain approximately 200 solar masses currently, and that photoevaporation removes mass at comparable rates to star formation. The star formation efficiency fraction of mass converted to stars rather than dispersed appears to be approximately 5 to 10%. This efficiency is modest compared to theoretical maximum efficiency approaching 100%, but typical for regions undergoing triggered collapse in photoevaporated clouds. The ultraviolet radiation that triggers collapse also disrupts it, dispersing envelopes before protostars can accrete their full potential mass. Additionally, stellar feedback from the first formed massive stars can disrupt further collapse in surrounding material. The result is that most mass in the pillars will be dispersed rather than incorporated into stars, though the minority that does form stars still produces hundreds of stellar systems. The mass distribution of forming stars shows that most detected protostars have masses between 0.3 and 3 solar masses, with fewer higher mass stars. The most massive protostar detected in JWST observations appears to be approximately 8 to 10 solar masses based on its infrared luminosity, substantial but far below the 50 to 100 solar mass monsters in NGC 6611, whose radiation shapes the pillars. The apparent lack of very massive protostars suggests that either such stars form rarely in triggered environments, or they form preferentially in different locations within the Eagle Nebula molecular cloud. The spatial distribution of protostars shows concentration near pillar tips and along pillar edges, exactly where photoevaporative compression is strongest. The densest concentrations appear at the tips of the main pillars, particularly the leftmost pillar where Hubble first identified evaporating gaseous globules. JWST's observations confirm that these EGGs indeed contain protostars, validating Hubble-era predictions that star formation was occurring in these structures. However, JWST also reveals protostars distributed throughout pillar interiors and along surfaces, indicating that star formation is more spatially extended than visible light observations suggested. The temporal evolution of the protostellar population can be inferred from the distribution of evolutionary classes. The relative numbers of class 0, I, and 2 sources suggest that star formation has been proceeding steadily over the past million years rather than occurring in a single burst. If star formation happened all at once, all protostars would be at similar evolutionary stages. Instead, the range of classes indicates continuous or episodic star formation with new collapse events occur. While earlier formed protostars continue evolving, this sustained activity suggests photoevaporative triggering operates continuously as radiation progressively penetrates the pillars. The eventual fate of forming stars involves dispersal from the pillars as the surrounding molecular material is removed by photoevaporation within a few million years. The embedded protostars detected by JWST will emerge as optically visible pre-main sequence stars, no longer associated with molecular clouds. They will become members of the NGC 6611 cluster, joining earlier formed massive stars in a bound or inbound stellar association. Follow-up studies of NGC 6611 stellar population can identify these future cluster members through their youth indicators, including rapid rotation, strong magnetic activity, and residual circumstellar material. The planet formation potential around these stars depends on disk survival during the final phases of photoevaporation. Circumstellar disks require several million years to form planets, but external photoevaporation can disperse disks in less time if radiation is sufficiently intense. The pillar's location, approximately 7 light-years from the main NGC 6611 cluster members, means ultraviolet flux is reduced by a factor of 50 compared to immediately adjacent regions. allowing disks to survive long enough for planet formation. Modeling suggests planets can form around most pillar-borne stars, though outer disk regions beyond approximately 50 astronomical units may be stripped by external photoevaporation. The protostellar population in the pillars of creation provides a unique laboratory for studying triggered star formation under controlled conditions. The triggering radiation source NGC 6611 is well characterized. The cloud properties are measurable through JWST and complementary observations. The resulting stellar population is observable through multiple evolutionary stages. This combination allows testing theoretical models of triggered collapse, comparing predictions for star formation rates, stellar masses, and spatial distributions against actual observations. The pillars thus serve as a benchmark case for understanding how massive star feedback influences subsequent stellar generations. Three-dimensional reality. Understanding the three-dimensional structure of the pillars of creation requires moving beyond the two-dimensional projection visible in images to reconstruct how material is distributed along the line of sight. This reconstruction uses multiple observational techniques including extinction mapping, kinematic measurements, and geometric modeling, each providing complementary constraints on the spatial configuration. The resulting picture reveals that the pillars are neither simple columns nor sheets, but rather complex three-dimensional clouds with substantial depth and internal structure. Extinction mapping provides the primary technique for three-dimensional reconstruction. The method uses background stars as probes, measuring how much each star is dimmed by intervening material. Stars directly behind dense pillar cores show high extinction, while stars passing through lower density regions or not intersecting the pillars show little extinction. By measuring extinction for hundreds of background stars distributed across the field, astronomers create a map of column density, the total amount of material along each line of sight. This column density map represents a two-dimensional projection of the three-dimensional density distribution. Converting column density maps to three-dimensional structure requires additional assumptions or constraints. The simplest approach assumes the pillars have specific geometric shapes, cylinders, ellipsoids, or tapered cones, and fits these shapes to the observed column density distribution. More sophisticated methods use the wavelength dependence of extinction, recognizing that different wavelengths probe to different depths. By comparing extinction measured at multiple wavelengths from near-infrared to mid-infrared, these methods can distinguish between material at different distances along the line of sight. JWST's multi-wavelength observations enable this tomographic reconstruction. At 2 micrometers, extinction is dominated by material in the nearest layers, approximately from 20 to 30% of the pillar depth. At 5 micrometers, one can see roughly halfway through. At 10 micrometers and beyond, the entire depth becomes transparent, and one observes integrated column density. By comparing extinction at these wavelengths and modeling light propagation through layered structures, astronomers constrain both the total column density and how it's distributed in depth. The results indicate that the main pillars extend approximately 1 to 2 light years along the line of sight, comparable to their widths perpendicular to our line of sight. This makes them roughly equidimensional rather than highly elongated structures oriented perpendicular to our viewing direction. The leftmost pillar appears to be about 1.5 light-years in depth, the middle pillar approximately 1.0 light-years, and the rightmost pillar between 0.8 and 1.2 light-years. These depths combined with the measured lateral widths yield volume estimates consistent with mass estimates from other methods. Kinematic measurements using molecular line spectroscopy provide additional three-dimensional information. Different portions of the pillars move at different velocities relative to Earth due to cloud turbulence, rotation, and expansion. By measuring the Doppler shifts of molecular emission lines, particularly carbon monoxide and molecular hydrogen, astronomers can determine line-of-sight velocities for different spatial positions. Material at different depths along our line of sight may have different velocities, allowing kinematic separation of foreground and background components. Ground-based submillimeter observations using the Atacama Large Millimeter Array ALMA measured molecular line emission from the pillars region at high spatial and spectral resolution. These observations show velocity gradients across the pillars, indicating rotation and systematic flows. The velocity structure suggests that material at the pillar tips is flowing away from us at approximately 5 kilometers per second relative to the pillar base is consistent with photoevaporative flow where heated surface material expands outward toward the ionizing radiation source is located in front of the pillars from our perspective. The three-dimensional orientation of the pillars relative to our viewing direction becomes determinable from combined morphological and kinematic analysis. The pillars point generally toward the northwest on the sky, in the direction of the main NGC 6611 cluster. The photoevaporation flow is predominantly away from us toward the cluster, indicating the ionizing sources are located somewhat in front of the pillars along our line of sight. Geometric modeling suggests the pillar axes are inclined roughly 30 to 45 degrees from the plane of the sky, neither perfectly perpendicular to our line of sight, nor lying in the plane of the sky. This orientation means we view the pillars from a moderately inclined angle rather than perfectly adjoint or face-on. Adjoint viewing would show the pillars as thin structures with maximum apparent length but minimum apparent width. Face-on viewing would show them foreshortened with maximum width but minimum apparent length. The intermediate inclination we observe shows comparable dimensions in both directions, consistent with the roughly equidimensional three-dimensional structure indicated by extinction mapping. The internal density structure shows systematic variations both laterally and in depth. The pillar cores where embedded protostars concentrate are the densest regions, with densities exceeding 106 molecules per cubic centimeter. These cores are typically small, measuring 0.01 to 0.05 light years, and are distributed along the pillar lengths at various positions. Surrounding the cores, intermediate density material at 104 to 105 molecules per cubic centimeter forms the bulk of the pillar volumes. The pillar surfaces exposed to ionizing radiation have somewhat lower densities, around 103 molecules per cubic centimeter, where photoevaporation has begun dispersing material. The depth variations show that density is not uniform along the line of sight but rather peaks at intermediate depths. Surface layers facing toward or away from us have lower densities due to photoevaporative erosion from both the front side radiation source and scattered radiation from other directions. The highest densities occur in more shielded interior regions where radiation has not yet penetrated and where compression from surrounding photoevaporation enhances density. This creates a shell-like structure with peak density not at the surface but slightly interior. The magnetic field structure within the pillars provides additional three-dimensional information from polarization measurements. Dust grains are not perfectly spherical but rather somewhat elongated, and they align with their long axes perpendicular to magnetic field directions due to interactions between grain magnetic moments and ambient fields. This alignment causes emitted thermal radiation to be partially polarized, with polarization direction perpendicular to the magnetic field. ALMA polarization observations of the pillars region show organized field structure generally aligned with the pillar axes. This magnetic field configuration suggests the fields are shaped by compression during photoevaporation. Fields oriented perpendicular to compression directions are enhanced, while parallel fields are relatively unaffected. The resulting field structure shows enhancement along pillar axes, providing some support against gravitational collapse perpendicular to the pillars while offering less resistance to collapse along the axis. This may explain why dense cores and embedded protostars tend to form in chains along the pillars rather than in isolated clusters. The three-dimensional density distribution enables calculating gravitational potential energy and comparing it to kinetic energy from turbulence and thermal energy from gas heating. These comparisons determine whether pillar material is gravitationally bound, whether gravity is sufficient to hold material together against dispersive forces, or whether photoevaporation will eventually disperse everything without further star formation. The calculations suggest that the densest cores are gravitationally bound and will complete collapse into stars. But the majority of pillar mass in lower density envelopes is marginally bound or unbound and will be photoevaporated. The filamentary substructure visible in high-resolution JWST images indicates that density variations occur at all resolved scales from light-year pillar dimensions down to 0.01 light-year filament widths. This hierarchy of structure suggests that turbulence operates across multiple scales, creating density fluctuations that gravity then amplifies in the densest regions. The three-dimensional distribution likely shows similar hierarchy. Large-scale pillar structures contain smaller-scale filaments which contain even smaller dense cores, with each level shaped by turbulence, magnetic fields, and self-gravity operating at the relevant scale. Comparing the three-dimensional structure to numerical simulations of photoevaporating molecular clouds shows general agreement in morphology and dynamics. Simulations that include turbulence, magnetic fields, self-gravity, and external ionizing radiation reproduce pillar-like structures with similar aspect ratios, density contrasts, and embedded dense cores. The simulations confirm that observed morphology is consistent with photoevaporation acting on turbulent magnetized clouds, validating the basic physical picture while highlighting that detailed agreement requires fine-tuning simulation parameters to match specific observed properties. Destruction timeline. The pillars of creation are not permanent structures but rather transient features in the ongoing process of molecular cloud destruction by newly formed massive stars. Understanding their eventual fate requires examining the physics of photoevaporation, measuring current destruction rates, and projecting forward to determine when the pillars will cease to exist as distinct structures. The timeline reveals that we're observing these iconic objects during a brief phase of their existence, with complete dispersal occurring within a few million years. Photoevaporation operates through absorption of ultraviolet photons from massive stars by neutral hydrogen at the cloud's surface. Each absorbed photon ionizes a hydrogen atom, breaking the bond between electron and nucleus. The freed electrons carry energy that heats surrounding gas to approximately 10,000 Kelvin, far above the roughly 100 Kelvin temperature in the heated molecular cloud interior. This heating causes gas pressure to increase by a factor of roughly 100, overwhelming gravitational binding and driving material to expand and flow away from the ionization front. The ionization front, the boundary between ionized and neutral gas, advances into the molecular cloud at a velocity determined by the balance between photoionization heating the front and recombination converting ionized atoms back to neutral. For the radiation field at the pillars of creation location, approximately 7 light-years from the main NGC 6611 cluster, the ionization front advances at roughly 10 kilometers per second. This corresponds to photoevaporating about 0.1 light-years per million years, or approximately 6,000 astronomical units per million years. However, the photoevaporation velocity represents the speed at which the ionization front moves into neutral material, not necessarily the rate at which visible pillar features recede. Dense regions resist photoevaporation longer than diffuse material, so the ionization front advances at different rates in different locations. Where density is high, the front advances slowly. Where density is low, it advances rapidly. This differential erosion is precisely what creates pillar morphology. Dense regions become pillars because they erode more slowly than their surroundings. Direct measurements of erosion rates come from comparing Hubble images from different epochs. The 1995, 2007, and 2014 Hubble observations span nearly 20 years, sufficient for measurable motion if structures change on century timescales. Analysis of these multi-epoch observations by Dr. Patrick Hartigan at Rice University identified small but significant changes in surface features, with some knots moving outward by approximately 0.01 arcseconds between observations. At the pillar's distance, this angular motion corresponds to approximately 60 astronomical units over 20 years, yielding velocities around 3 astronomical units per year, or about 14 kilometers per second. These measured velocities slightly exceed the theoretical ionization front velocity of 10 kilometers per second, possibly indicating that measurements capture both ionization front motion and hydrodynamic flow of already ionized gas accelerating away from the cloud surface. The material at pillar surfaces first becomes ionized and heated, then accelerates as pressure gradients push it outward, reaching terminal velocities of 15 to 20 kilometers per second in the fully ionized flow away from the cloud. The observed velocities represent some combination of front motion and material acceleration. Projecting forward using measured erosion rates allows estimating how long the pillars will persist. The main leftmost pillar currently extends about 4 light-years from base to tip. If the tip recedes at approximately 10 kilometers per second, 0.03 light-years per thousand years, the pillar will shorten by roughly 1 light-year in 300,000 years. However, photoevaporation doesn't just erode tips, it attacks pillar surfaces from all sides simultaneously. Lateral erosion will thin the pillars over comparable timescales, eventually fragmenting them into disconnected clumps. The timescale to complete dispersal depends on pillar width. The leftmost pillar is approximately 1 light-year wide, so erosion from both sides at 10 kilometers per second will consume the entire width in approximately 300,000 years if density remains constant. However, density increases toward pillar centers, slowing erosion as the front advances. Accounting for density, structure extends dispersal timescales to roughly 1 to 2 million years before the densest cores are exposed and photoevaporated. Comparison with the pillar's age provides context. The NGC 6611 cluster that provides ionizing radiation formed approximately 1 to 2 million years ago based on stellar age measurements. The pillars themselves likely began forming around this time as photoevaporation carved the molecular cloud. If the pillars are roughly 1 million years old currently, and will persist for another 1 to 2 million years before complete dispersal, their total lifetime spans approximately 3 million years. We're observing them somewhere in the middle third of this lifetime past their formation epoch but well before their destruction. The internal destruction timeline differs from external photoevaporation because it involves stellar feedback from the embedded protostars themselves. As protostars within the pillars grow and eventually begin nuclear fusion, they generate ultraviolet radiation and stellar winds that will disperse their immediate surroundings from within. The most massive protostars detected in JWST observations, those with 8 to 10 solar masses, will reach main sequence and begin generating significant ionizing radiation within approximately 100,000 years. Comparable to or faster than timescales for external photoevaporation to penetrate to their locations. This internal feedback creates a race between external destruction and internal disruption. If external photoevaporation disperses material before embedded protostars reach main sequence, those stars emerge into cleared regions and join the cluster as normal stars. If protostars reach main sequence while still deeply embedded, they create small high regions, bubbles of ionized gas that expand and merge with the larger ionized volume, essentially assisting external photoevaporation in destroying the pillars. Either way, the pillars are doomed within a few million years. The intermediate timescales, hundreds of thousands of years, will see significant morphological evolution as photoevaporation proceeds. Computer simulations of photoevaporating pillars show that as erosion advances, new dense cores become exposed as overlying material is removed. These newly exposed cores can become the tips of new smaller pillars or can appear as isolated globules. Meanwhile, current pillar tips may erode away or fragment as supporting material is removed. The specific pillar morphology we observe today will transform into different configurations while the general character of pillar-like structures persists. Evidence for ongoing evolution appears in JWST observations showing features at various stages of dispersal. Some small-scale structures visible in JWST images appear to be fragmenting, evaporating gaseous globules that are becoming disconnected from parent pillars as connecting material photoevaporates. Other features show cometary morphology with dense heads and trailing tails, indicating material flowing away from condensations as they erode. These features provide snapshots of structures at different points in the destruction sequence. The evaporating gaseous globules EGGs identified in Hubble images and confirmed by JWST represent small-scale structures with particularly short lifetimes. The typical EGG measures roughly 1,000 astronomical units across and contains approximately 1 solar mass of material. At photoevaporation rates of 10 kilometers per second, such structures will be entirely dispersed within approximately 30,000 years. The embedded protostars within EGGs must complete most of their mass accumulation within this window or be exposed while still forming, potentially limiting their final masses. The role of instabilities in accelerating destruction deserves consideration. Photoevaporating flows are susceptible to various instabilities: Rayleigh-Taylor instabilities, where light fluid accelerates dense fluid; Kelvin-Helmholtz instabilities at shear boundaries between flowing and static material; and thermal instabilities in radiatively cooling gas. These instabilities can fragment smooth surfaces into complex structures, potentially accelerating mass loss beyond what smooth photoevaporation from advance would predict. Evidence for instabilities appears in the intricate small-scale structure visible on pillar surfaces in JWST images. The broader Eagle Nebula evolution contextualizes the pillar's destruction timeline. The entire molecular cloud complex is being photoevaporated and disrupted by NGC 6611, with the process more advanced in regions immediately adjacent to the cluster and less advanced in distant regions. The pillars of creation occupy an intermediate zone where photoevaporation is well underway but not yet complete. In regions closer to the cluster, molecular material has been almost entirely dispersed, while more distant regions retain larger molecular cloud masses with less developed pillar morphology. Extrapolating forward 5 to 10 million years, essentially all molecular material in the Eagle Nebula will be dispersed through photoevaporation. The region will appear as an expanding high region, a bubble of hot ionized gas surrounding the NGC 6611 cluster. The young stars currently embedded in the pillars of creation will have emerged and become visible cluster members. The spectacular pillar morphology will be gone, with only historical images and scientific papers preserving knowledge of structures that once existed in this now cleared region. This timeline makes the pillars of creation simultaneously ephemeral and significant. Ephemeral because their existence as distinct structures spans just a few million years, brief even on stellar evolution timescales, negligible cosmically. Significant because they represent a key phase in star formation when molecular clouds transition from dense, actively star-forming structures to dispersed, exhausted regions. Understanding the pillars illuminates how massive star feedback terminates star formation and how the cycle of cloud formation and destruction perpetuates across galactic history. The human perspective on these timescales evokes interesting reflections. The pillars existed essentially and changed throughout all of recorded human history. They were destroying and forming stars before humans evolved, before dinosaurs existed, even before Earth's current continents formed. They will continue essentially unchanged for far longer than civilization has existed. Yet from the universe's perspective, they are momentary structures, here briefly and gone quickly in the ongoing cycling of matter between diffuse and dense, molecular and ionized, cloud and star. Hidden populations. JWST's infrared observations revealed stellar populations within the pillars of creation that were completely invisible to Hubble, fundamentally changing our understanding of star formation activity in the region. The term hidden populations encompasses multiple categories: deeply embedded protostars still accumulating mass from surrounding envelopes, older pre-main sequence stars with moderate dust obscuration, background field stars lying behind the pillars, and even potential planetary mass objects. Each population provides different insights into the region's star formation history and current state. The deeply embedded protostellar population represents the most scientifically valuable hidden component. These objects class 0 and early class 1 protostars are so enshrouded in dense envelopes that visible and even near-infrared light cannot escape. Only at wavelengths beyond approximately 3 micrometers does emission from heated dust in the envelope become detectable. JWST's coverage from 0.9 to 21 micrometers includes these longer wavelengths, enabling detection of sources Hubble completely missed despite its 2014 infrared observations extending only to 1.6 micrometers. The census of embedded protostars increases dramatically with JWST. Hubble's 2014 infrared observations detected approximately 70 sources within the main pillar region. JWST's NIRCam observations detected approximately 300 sources in the same area, more than a fourfold increase. These additional detections are not simply fainter versions of sources Hubble saw, but rather categorically different objects visible only at the longer wavelengths where JWST operates. Many sources bright in JWST's 4.4 micrometer images are completely absent in images at shorter wavelengths, indicating extreme dust obscuration. The spatial distribution of newly detected protostars shows concentrations in precisely the regions Hubble images indicated were densest. The pillar tips where Hubble detected AGGs now show clusters of embedded sources 5 to 15 protostars concentrated in regions of 0.05 light-years extent. The pillar interiors, which appeared largely empty in Hubble images except for scattered surface features, now show dozens of embedded sources distributed throughout. Even regions appearing relatively transparent in JWST's near-infrared images harbor deeply embedded sources visible only in MIRI observations. The luminosity distribution of detected protostars spans nearly 6 orders of magnitude from the brightest sources at approximately 1,000 solar luminosities to the faintest detections, around 0.01 solar luminosities. This range reflects the broad range of protostellar masses from potential brown dwarfs below 0.1 solar masses to massive protostars exceeding 10 solar masses. The luminosity function, the number of sources at each luminosity, shows the expected power law distribution at high luminosities and tentative flattening at low luminosities. Though JWST's detection limits prevent measuring the function for the lowest luminosity sources, the evolutionary classification of detected sources relies on spectral energy distributions, how brightness varies with wavelength from near to mid-infrared. Class 0 sources show rising spectral energy distributions, brighter at longer wavelengths because cool envelope emission dominates over hotter stellar photospheric emission. Class 1 sources show flatter distributions as stellar emission becomes more comparable to envelope emission. Class 2 sources show declining distributions at mid-infrared wavelengths as the stellar photosphere dominates, and only a thin disk contributes infrared excess. JWST's multi-wavelength coverage enables classifying sources reliably. The ratio of evolutionary classes provides insights into star formation history and timescales. If star formation occurred as a single burst, all protostars would be at similar evolutionary stages. Instead, JWST detects sources spanning all classes from 0 to 2, indicating sustained or episodic star formation over timescales exceeding 1 million years, the total duration from class 0 to class 2. The relative numbers suggest approximately 30% class 0, 40% class 1, and 30% class 2, though these percentages carry significant uncertainty from incompleteness at low luminosities and potential source confusion in crowded regions. The pre-main sequence stellar population stars that have dispersed their envelopes and are contracting toward the main sequence but have not yet begun core hydrogen fusion represents another hidden component partially revealed by JWST. These sources have masses and luminosities similar to class 2 objects but lack significant infrared excess from circumstellar disks. They appear as relatively blue near-infrared sources, distinguishable from foreground and background field stars through their spatial clustering with confirmed protostars and through spectroscopic signatures of youth, including strong lithium absorption and rapid rotation. JWST detected approximately 100 candidate pre-main sequence stars within the pillar region, identified through photometric selection based on colors and magnitudes consistent with lightly obscured stars at the Eagle Nebula distance. Spectroscopic follow-up using JWST's near-infrared spectrograph confirmed approximately 30 of these candidates showing spectral features including strong molecular hydrogen emission, forbidden light emission from shocks, and absorption features consistent with young stellar photospheres. These confirmed young stars represent the population that formed slightly earlier than the currently embedded protostars, perhaps 1 to 3 million years ago, and have now emerged from their natal cocoons. The brown dwarf population objects with masses below approximately 0.08 solar masses, insufficient to sustain hydrogen fusion, remains largely undetected even at JWST observations. Brown dwarfs in the pillars region would have ages around 1 million years, making them extremely faint with luminosities around 0.01 solar luminosities or less. At the Eagle Nebula distance, such objects would have infrared magnitudes around 23 to 25 near or below JWST's detection limits in reasonably short exposures. Detecting the pillar's brown dwarf population will require dedicated deep observations with integration times exceeding those allocated for the current observations. Free-floating planetary mass objects, brown dwarfs below roughly 5 Jupiter masses, are even more challenging to detect but might exist if they form through gravitational fragmentation of molecular cloud material or through dynamical ejection from protoplanetary disks. Ground-based infrared surveys of young star-forming regions have detected a few such objects, establishing that they exist in at least some regions. Whether the pillars of creation harbor planetary mass objects remains unknown, awaiting deeper observations or alternative detection methods like microlensing surveys. The background stellar population field stars lying behind the pillars of creation provide scientifically valuable information by serving as probes of pillar structure. Through differential extinction, JWST's observations enable measuring brightnesses and colors for several hundred background stars distributed across the field. These stars span a range of intrinsic colors from hot blue stars to cool red giants, with known color magnitude relationships allowing photometric distance estimates. Stars confirmed to lie beyond the Eagle Nebula based on distance and proper motion provide clean extinction measurements uncontaminated by uncertain intrinsic properties. The extinction map derived from background star photometry shows structure on scales from light-years down to 0.01 light-years. Large-scale gradients reveal the overall pillar morphology, with extinction exceeding 10 magnitudes in visual wavelength equivalence in the densest cores and dropping to near zero outside the main pill. Lower boundaries. Small-scale variations show filamentary structure, dense knots, and irregular features indicating that density is not smoothly distributed but rather shows significant substructure created by turbulent and gravitational instabilities. The foreground stellar population stars between Earth and the pillars of creation contaminates the protostellar population counts unless properly identified and removed. Foreground stars appear bluer than embedded protostars because they suffer little or no extinction from intervening material. However, some foreground stars might be intrinsically red, mimicking embedded sources. Distinguishing foreground stars requires combining photometric colors with proper motion measurements. Foreground stars show larger proper motions than distant Eagle Nebula members, because nearby stars' tangential velocities produce larger angular motion on the sky. Gyrostrometry provides proper motions for the brightest sources in the pillar's field, enabling identification of foreground contamination. Approximately 10 to 15% of sources initially classified as embedded protostars based on infrared colors show proper motions inconsistent with Eagle Nebula membership, revealing them as foreground dwarfs. Removing these contaminants refines the true protostellar population and improves understanding of star formation rates. For fainter sources below GIS detection limits, statistical foreground subtraction methods estimate contamination based on stellar density models. Extragalactic background contamination represents another potential source of confusion. Distant galaxies can appear as point sources in JWST images and might have infrared colors overlapping with embedded protostars if the galaxies contain active star formation producing strong dust emission. However, galaxies are typically more extended than point-like protostars, enabling morphological separation. Additionally, very few galaxies exist at the specific infrared color and magnitude combinations characteristic of young embedded protostars, making contamination negligible for most sources though potentially significant for the reddest, faintest detections.